What if error was not measured by a ruler, but by the curve you are learning from? That is the idea behind Bregman Divergence, a geometry of mismatch built from one convex function. Start with a bowl-shaped function phi. Pick a point Q. Now draw the tangent line to phi at Q. At another point P, compare the real height phi of P with the height predicted by that tangent. The vertical gap is the Bregman divergence. In symbols, d phi of P and Q equals phi of P minus phi of Q minus the gradient of phi at Q dotted with P minus Q. That last part is just the best local linear prediction from Q. So the divergence asks, how much did the curve surprise the tangent? If phi of x is 1/2 x squared, the gap becomes ordinary squared distance. But with different phi, the same recipe creates famous learning losses. For probability vectors, choosing negative entropy gives KL divergence, the surprise cost when one distribution is used in place of another. This is why Bregman divergence appears in optimization, clustering, and machine learning. It lets the loss match the shape of the data space instead of forcing every problem to look Euclidean. There is one catch: it usually is not symmetric. Going from Q to P can cost a different amount than going from P to Q, because the tangent is drawn at the starting point. So the vivid picture is simple: choose a convex landscape, draw a tangent, and measure the gap. That gap is a customized notion of error. Bregman divergence is not just distance. It is distance with a memory of curvature.